As you know, in alkene addition reactions, if you do a hydrohalogenation like in reaction A, or if you do a acid catalyzed hydration like in reaction B, you go through a carbocation intermediate. Now, when you form a carbocation, there is a possibility that you can do also a carbocation rearrangement. And in this video, I want to go over some problems that can help you be able to predict what kind of alkenes can go through this carbocation rearrangement and also look at some of their mechanisms. For instance, what if the problem was draw the major product? This is an example. Draw the major product. The major product, if you're doing a hydrohalogenation or a acid catalyzed hydration, major product will often come from the most stable carbocation formed. And if I give people this alkene and react it with HCl, if you're having trouble copying or keeping up, go ahead and pause the video. But normally, you have to decide, is the chlorine going to go on that carbon or this carbon? One of the carbons of the double bond. Because you know from Markovnikov's rule, you want to form the more stable carbocation. And okay, so I'm not drawing the product. This is like scratch paper, but I want to draw the carbocation intermediate. And the carbocation intermediate would be this, and the plus charge would be here. Intermediate, so I'll put it in brackets. Again, this is following Markovnikov's rule. And if there was no carbocation rearrangement, then the chlorine would go right there. The chlorine would go right there. A couple things. Markovnikov's rule, if you don't remember, I like to think of it as the rich get richer. The rich get richer, and the money is hydrogen. So if you look at this double bond, there are two hydrogens on this carbon. I'll put a dot here. And there's one hydrogen on this carbon. So this carbon is richer in hydrogen, so it gets the third hydrogen, and that's why this is a CH3 group. This carbon here doesn't get anything, so it's naked, and it only has 3 bonds. So again, I like to say the rich get richer. Find out which carbon has more hydrogens, and that's where this hydrogen goes. We form a secondary carbocation. And where am I going to write that? Secondary carbocation. Again, if there was no carbocation rearrangement, then just put the chlorine right here, and that's your final product. The other thing is that, if we had put the hydrogen on this carbon, on the opposite carbon, then we would have had a primary carbocation. And I like to say you should never form a primary carbocation because they're not stable. But again, we're concentrating on rearrangements. And the rearrangement in this case will be a shift because we have a secondary carbocation, but if you know your structures well, your line structures, you know there's a hydrogen right there. And by doing a little jump, and so this is a mechanism arrow, by doing a jump, by showing the electrons bring the hydrogen nucleus to this carbon, look at the result. The result is now what? Since the hydrogen went on this carbon, that carbon is no longer naked and it has 4 bonds, so that carbon is neutral. But now this carbon in the middle is naked and it's positively charged. So that's another intermediate. I would say that this is the initial carbocation, and it happens to be secondary. But here we have a tertiary carbocation, which is stable, much more stable than a secondary. And when I said the major product, for a reaction that goes through a carbocation, most cases the major product will come from what? The more stable. I was going to say stabler, but I wrote it down by the more stable carbocation. So, like, I'm not drawing any mechanisms. I'm just showing you the intermediates. The final answer if I wanted to draw the major product, would be this. The chlorine's there. That's unusual because you would have expected the chlorine to go here, right? So another way that they could ask this problem is if they say, how did this happen? Then the professor is implying that you should draw the mechanism. You should draw the mechanism. Because, again, the chlorine's ending up on the carbon that wasn't part of the double bond. Okay? Now, before we move on, this is a special type of shift. It's called a hydride shift. And how am I going to put this? Well, I'll just put it underneath here. Hydride shift. You're shifting a hydrogen, but they call it a hydride because you're shifting the electrons as well, and you're shifting 2 electrons. So what's a hydrogen with 2 electrons? It's negatively charged. That's called a hydride. You know what this is not? This is not a proton transfer. So this is not that's called a proton. You do that when you have acid-base chemistry. Okay? And the last thing I want to add here is this is an equilibrium, but it's more favored towards the tertiary carbocation. The reason why I did a carbocation rearrangement here is that I realized that my initial secondary carbocation can be made more stable by converting it into a tertiary carbocation by just doing one shift, by shifting one thing. And the thing that I shifted was this hydrogen with its electrons, which is technically a hydride. This gets a little bit hairy because I think students are tempted to do, let me just shift all over the place, and let me just keep shifting until I finally get a tertiary carbocation. There are some ground rules, though, when you are doing a carbocation rearrangement, and they're a little bit subtle. Let me write them down. If if you're asked to provide the product, then don't go shifting all over the place. You only should shift only once. So if asked for the major product, for the vast majority of cases, a professor is expecting you to do one one shift, but that's only if you could make it a better carbocation. I have to always give that caveat that you only do the shift if you could make a better carbocation. If asked for the major product and you think a carbocation rearrangement occurs, do what? Do only one shift. And if that one shift doesn't get you a better carbocation, then don't do the shift at all. Okay? Do only one shift, and that shift can be either a hydride shift, which we just did, and the second most popular, the other most popular shift is called a methyl shift. Now, those of you who maybe read the textbook or looked up some new other problems, you could also do what's called a ring expansion. We're not going to talk about ring expansions in this case, but those are the ground rules when I give a problem like this. If I expect the student to give me the major product, okay, and they think there's a carbocation rearrangement, you could only do one shift and it's either hydride or methyl. So you might ask, well, what other kind of problem is there? When would you not ask for the major product? This is in contrast. So contrast this problem here, draw the major product, with the problem that I'm about to show. Another problem, and this is going to say, how is C formed, question mark. See, in this problem, you're given the starting material. Okay. Again, let me draw out the reaction, and you could pause and copy this. See, in this type of product, sorry, this type of problem, you are given the products. And if you are given the products, you do whatever it takes to draw the mechanism to get to the product they want formed. And look at this product here that I'm about to form. I think you could guess the weird looking one is this one. This is C. This is B. And this is A. Because, again, with an addition to an alkene, you expect the bromine to either go here or here. The thing is, when looking at this problem, we can't use Markovnikov's rule because both carbons are equally rich. And that's why some products, you have the bromine on this carbon. That's where the carbocation was. And other times you have the bromine on this carbon because that's where the carbocation formed. I'm not going to say 50-50 because you do have some of this third product. But you notice where the bromine added? Not only did the bromine not add to one of the double bond carbons, but look, it lost a methyl group. We had two methyl groups here. And now we have one here, one methyl, down here, and one methyl, excuse my handwriting, up there. You know what that suggests? That suggests that there was a methyl shift. And in this case, you're not relegated to only one shift, okay? Now that we're given the product, you do whatever it takes in a mechanism to get to that product, okay? So let me show you this. Now, I'm still thinking that we're going to go eventually from a secondary carbocation to a tertiary carbocation. I mean, that's the motivation, that's the driving force for this shift. Now again, if we can never get that tertiary carbocation, then don't do shift at all. Okay? But here, I think we could safely assume there's a shift because the bromine ended up in such a weird place and the methyl group actually moved. Okay. When you draw the mechanism, you want to be very precise. Draw the starter material first. And how do I want to do? Start out. You want to show every bond that's made and every bond that's broken. And I believe you were taught that for these addition reactions, the pi bond attacks the hydrogen, except bromine. I normally don't care if there's a full arrow or equilibrium arrow. If it was an acid-base reaction, I would use equilibrium, but for the most part, I use just a regular arrow. Okay? And you know that we normally would use Markovnikov's rule, but you know the carbons are equally substituted, so there is no rich in the rich get richer. I have to focus on this, and I'm thinking that does it really matter? Yeah, I'm thinking that if I put the carbocation here, okay, I am closer to getting this to shift than if I put it over here. Okay? And you'll see what I mean once I shifted that methyl group. But the thing is, there's your secondary product because we kicked out a bromine. The thing is, we have a secondary carbocation. I'm not going to write carbocation anymore. I'll just put secondary. You know, I could put the bromine here and I get product A. Okay. If I put the carbocation here initially, I get product B. It looks like I got to get the carbocation right here on that carbon. So I'm not that close actually, but I can try to walk it over by doing a first hydrogen shift. So this is what I mean by you could do multiple shifts if you're given the product. And maybe I'll put equilibrium because it is actually an equilibrium. You could shift backwards as well. Okay, so do you see how now I get the carbocation on this carbon because now this carbon is neutral. Okay, that was a hydride shift. Okay, we moved a hydride shift, but honestly, it didn't really do much except get the charge closer to this position because we went from a secondary to a secondary. Okay, so again, if you were given this problem and you weren't given the products, I personally would not do any kind of shift. And I would draw both of these two. They ran the experiment. They said, we got a little bit of this, show how it happens. All right. So now look at this. We have a juicy spot here because if I remove one of these methyl groups, I get a tertiary carbon. So I get a carbon that could have a plus charge here. So this, actually, let me draw the product first. And now this one, the equilibrium arrow is now favoring the product Y because now it's tertiary. Now it's tertiary. So yeah, I just shifted that methyl group. So let me put a dot here. So that's the methyl group with a dot. I shifted it over, and now the methyl group is over there. So this is good because we went from a secondary to a tertiary. This is called a methyl shift. So we had a hydride shift here. This is a methyl shift. Okay. And what's the last step? Right, the last step is the Br minus. Now I like to use the lone pair. I don't ever like to draw the mechanism arrow from the charge, even if it's a negative charge. I like to draw it from electrons, visibly electrons, either a lone pair or a bond. That's how I start my mechanism arrow. But anyway, did we get the product now? We have this, and we have that. Okay, there's your product, and we did a, I'll label it, what happened here? Hydride shift. Okay. So there's your full mechanism to get product C. What is the key? Okay, let's go back. Like, how did I know a shift would occur here? I didn't know. I had to draw the intermediate first, and not just the intermediate. I had to draw the initial carbocation. And then when I look at the initial carbocation, which is secondary, I asked myself, can I stop there? Can I add the Cl now? Or is there a possibility to get a better tertiary carbocation with what? With only one shift. Again, these are the ground rules. And I think most professors would agree that they don't want you shifting all over the place if you're not trying to hit a target. If you're trying to predict a carbocation rearrangement, only do one shift. Okay. Uh, I have more examples. I am going till 25 minutes at least because I want to make sure that you've seen the main examples for hydride shift and methyl shift. So here's a reminder that don't forget, there are probably two reactions that you know that can possibly undergo a carbocation rearrangement. So don't forget other reactions that go through a carbocation rearrangement. Oh, let's get rid of the word rearrangement. Don't forget other reactions that go through a carbocation. And then, since it can go through a carbocation, you have to consider, is it possible to do a rearrangement? Let me give you an example. We're going to do examples until we recognize the tricks to figure out whether a rearrangement can occur. So in this case, HCl. HCl is hydrohalogenation, and it does go through a carbocation. But also acid catalyzed hydration, and many times they draw the reagents like this, H2SO4. Sometimes they add, do they add heat? Normally they don't add heat actually for acid catalyzed hydration. Why hydration? You're adding an H and an OH. So you're adding water, but in the form of a hydrogen and an OH, a hydroxyl group. Not a big deal. The big deal is will this go through a carbocation rearrangement? All right. You want me to go through the mechanism for this? It's basically the same thing as this, but I'll go through the mechanism. And then I'll tell you what's the shortcut to figure out whether you're going to do a shift or not. So most cases your professor will say that if you add any acid to water, it is allowable to use the hydronium ion, H3O+. Because in real life, when you mix a little bit of sulfuric acid in water, like water's a solvent, this is a strong acid, so it's going to lose, each molecule of this is going to lose one proton. And really, the acid you really have, once you mix these two, is this. Right, the water will pick up a proton from sulfuric acid. So here's the mechanism. Protonate, or you could say the alkene attacks, and you have this. Where do you think the plus charge goes? Well, the hydrogen goes to the richer carbon. The rich get richer. This has 2 hydrogens, this has 1. So this hydrogen goes to this carbon. The other carbon got nothing. That's where the plus charge is. Okay? And I do like to draw the secondary, I call it the secondary product, even though we're not going to use it in the next step. Because in the next step, this is the trick. The trick is to realize that the initial carbocation is secondary. If you could get there, then you could ask yourself, can I make it tertiary? And yes, we can make it tertiary by, see, there's no hydrogen here, so we can't do a hydride shift. There's a methyl group, and again, you are allowed to do either a hydride shift or a methyl shift. Now, would you want to do an ethyl shift or a propyl shift or even a phenyl shift? Normally, no. But again, if you're given a product where you feel like you have to do one of those more exotic shifts, or whether you have to do multiple shifts, then do it. But again, if you're just predicting the product like we're trying up here, oops, why did it go dark? Like we're trying up here, then you only do one shift, and that's the shift I'm doing. Can you predict the product here now, the intermediate? See that methyl goes to this carbon, so we'll put a methyl there. This methyl still exists, okay? And now the plus charge is the carbon that only has 3 bonds, which is this one. And there you go. We have a tertiary. Shall we finish the mechanism? The mechanism is a little bit longer than a hydrohalogenation because after this attack, okay, try to make it clear for the grader that that they know which carbon you're adding the oxygen to. This is a little bit iffy, but I think it's just good enough to know that that arrow is headed for this carbocation. Okay. Make it clear for the grader. Make it easy for them. Now, we'll bring in both hydrogens to the bonding party. I never indicated that I broke an oxygen-hydrogen bond. So you got to show in the intermediate both hydrogens, and you know that oxygen with 3 bonds and 1 lone pair is positive. It's 1 lone pair because we used the second lone pair to make the bond itself. Oh, and what else did I forget? I forgot this methyl group. And then lastly, we got to deprotonate that to make the what? To make the alcohol. Remember, this was acid catalyzed hydration. Okay, so I drew the OH down here. To me, that doesn't look great. Let me put the OH up here. It's still the same product. And then I do have this methyl group here. I forgot the methyl group temporarily, so I'm kind of nervous. Let me count, especially since we moved a methyl group. I don't want to lose any carbons. 1, 2, 3, 4, 5, 6, 7. So this is a C7 alkene, or C7 molecule. Over here, 1, 2, 3, 4, 5, 6, 7. Great. I didn't lose any carbons. Okay. And then we regenerated H3O+. So again, I like to put the secondary product. But here's your product, and this is the mechanism, right? But would you be able to draw the product without having to draw the mechanism? What if they only asked you to draw the product, the major product? Okay, let me draw actually what we have in the mechanism, like this. Okay, and by analogy, this hydrohalogenation would also go through the same methyl shift. Oops, and now we put a chlorine instead of the OH. Okay, what's the shortcut? What if I don't want to draw a mechanism and use up that time? The shortcut is this. Draw the initial carbocation, either on a scratch sheet of paper or underneath, because the initial carbocation would be this, right? The plus charge goes on this green arrow. And that's for both cases, right? When this attacks the hydrogen, the plus charge will go here. If it's a secondary carbocation, kind of be on the lookout. Can I move anything, a hydrogen or a methyl, to make it tertiary? That's the trick. Okay, so without having to go through the whole mechanism, draw the intermediate, the initial intermediate, and ask yourself if you can make that secondary carbocation into a tertiary. Okay. Is there any other example? Why don't I leave it at that? Okay, because we saw an example of a hydride shift, and we saw an example of a methyl shift here. Okay. Actually, off the top of my head, let me go through a couple of molecules that would go through a shift. Something like this. I chose a hard example actually. This. Okay. It's symmetrical, but you realize that if I'm doing either hydrohalogenation or acid catalyzed hydration, it actually doesn't matter which carbon gets the carbocation because it's symmetrical. So let me put the carbocation here, and now you notice that you can do a hydride shift. Okay, and I'll let you do that on your own. The classic examples were what? Do you notice that in my first example we have a terminal alkene and a crowded carbon next door? Over here, a terminal alkene and a crowded carbon next door. An opportunity to get that plus charge into a tertiary carbon. So right now it's quaternary. There are 4 carbons attached to this, but by moving the methyl group, I got the tertiary. So other molecules just simply could look like this, right? That would go through a hydride shift. A molecule like this, are you seeing the pattern? That would go through a methyl shift, right? I could take this molecule here, and what if instead of going, see, it would go through a hydride shift here. Let me draw it actually, here. But what if there was no hydrogen there? What if I did this? That would go through a methyl shift. There are actually a lot of examples if I'm just limiting ourselves to methyl and hydride shifts, but that's 80%, 90% of the carbocation rearrangements that you will see. Okay. Again, for the more exotic, like a ring opening or ring expansion, don't worry about it. Okay. Worry about the hydride and methyl shifts and trying to get a secondary carbocation to be a tertiary.